Now in this video, we are going to revise the formulas that are coming under properties of soil, compressibility and consolidation, and this shear strength from soil mechanics. Now let's start with properties of soil. There are many properties of soil. Now let's see one by one. So first property is the water content, and it is given by the ratio of weight of water to the weight of solids, and it shall be greater than or equal to 0. And next, degree of saturation, and it is given by the ratio of volume of water to the volume of voids, and it has range from 0 to 100% or 0 to 1. And void ratio, an important property, that will be given by the ratio of volume of voids to the volume of solids, and it shall be greater than 0, and it has no upper limit. And porosity is also related to the void ratio only, but only difference is void ratio takes volume of solids only into its account, but porosity total volume. So that's why n is equal to the ratio of volume of voids to total volume of soil, and it has the range of 0 to 100%. And air content, what is air content? Ratio of volume of air to volume of voids. So it has also the range of 0 to 100%. And percentage air voids, that is n suffix a equal to va by v, and it has range of 0 to n. So 0 to n, this is the percentage air voids. You can refer this three-phase diagram of three-phase block diagram of a soil sample. In a soil sample, we have solid content, we have voids. In voids there can be water and there can be air, and in the left side we can take volume, and in the right side we can take the weight. So this is a three-phase diagram. A soil sample can have two phase and three phase diagram only. When it can have two phases only, it has solid and air or solid and water. And this is the three phase diagram having all the three, solid, water and air. So these are some important properties. Now we shall see formulas regarding unit weights. There are many types of unit weight: bulk unit weight, dry unit weight, saturated unit weight, submerged unit weight. So first, bulk unit weight is given by the ratio of total weight of soil sample divided by total volume of soil sample, and it has units kilonewton per meter cube. And dry unit weight, gamma d is equal to W dry, that is dry weight of soil sample divided by total volume. And in case of saturated unit weight, simply saturated weight of soil sample divided by total volume. And submerged unit weight, submerged weight divided by total volume, and it can also be given as saturated unit weight minus gamma W. What is gamma W? Unit weight of water. And unit weight of water is given by weight of water to the volume of water, and it has a value of 9.81 kilonewton per meter cube, or we can say 1 gram per cc. If you are calculating in terms of grams and centimeter cube, it can be 1 gram per cc. So gamma is the unit weight, but if we want to say in terms of density, we can call it as rho. That is, for example, bulk density is rho is equal to W by V, and it has the unit of gram per cc or kilogram per meter cube, like that. So these are some important formulas regarding unit weights. And the most important thing is unit weight of solids. So how to calculate that unit weight? Gamma S is equal to Ws divided by Vs, weight of solid content, only solid content, divided by volume of only solids. So that gives the unit weight of solids. And the specific gravity of the solid, that is Gs, has the range of 2.65 to 2.8. We shall see more about specific gravity formulas in the upcoming slides. And we shall see now the important relations between previous formulas, that is unit weight and properties. First is weight of solids. Ws is given by W by 1 plus Wc. What is simply W? So total weight. So how to calculate weight of solids only? Ws is equal to W by 1 plus Wc. Wc is water content. And N is, and the relation between porosity and void ratio is given by this. N is equal to E by 1 plus E, or E is equal to N by 1 minus N. And Wg equal to Se. This is a basic and important formula or important relation in the properties. and S is the degree of saturation, E we know void ratio, G is the specific gravity, and W suffix C is the water content. And these are some relations regarding densities, or we can say unit weights. So gamma sat is equal to G plus E divided by 1 plus C gamma W. Actually base equation is this one. This is the base equation, or we can say bulk unit weight equation. So bulk unit weight is given by G plus SC by 1 plus C gamma W, and in case of full saturation S is 1, so that's why here G plus 1 into E, so that's why G plus SC by 1 plus C into gamma W. And in case of dry state, degree of saturation is 0, so that's why G gamma W by 1 plus C. And in case of submerged state, it shall be like this, G minus 1 by 1 plus C into gamma W. And it ranges like this, or we can say in terms of ascending order, gamma hat is the maximum value, gamma hat has the maximum value, followed by gamma T, that is bulk unit weight, followed by dry, followed by submerged. So that means submerged unit weight has the least value, and saturated unit weight has the greatest value, and the gamma S is nothing but unit weight of solids, solids only. This has the greater value than gamma sat. When we compare this and gamma sat, gamma S value is greater than gamma sat value. And there are some other relations between dry unit weight and bulk unit weight. So how it is related? Gamma D is equal to gamma T by 1 plus WC. So by using this relation, we can find other value. And gamma D is also can be given as 1 minus NA. What is NA? Percentage air voids into G rho W by 1 plus WC, or gamma W, anything. So gamma D is equal to 1 minus NA G gamma W by 1 plus WG. And there is another relation like this, bulk unit weight, dry unit weight, saturated unit weight. So all three things together, how it is related. So gamma is equal to, or gamma T, we can say bulk unit weight equal to gamma D plus S into gamma sat minus gamma D. So this is an one relation regarding all the three terms, bulk unit weight, dry unit weight, and saturated unit weight, how it is related. So these are some important relations regarding unit weight and some properties of soil. And we shall see another important thing called borrow pit problem. So borrow pit problem, we shall follow this equation only. From this equation we can get the other value, like if we know the gamma D1, that is borrow pit's dry density, we can get the answer for gamma D2, that is filling embankment density, soil in embankment. So gamma D1 is borrow pit, gamma D2 is for embankment, and same likewise V1 is volume in borrow pit, volume of soil taken from borrow pit, and V2 is the volume of fill in embankment, and E2 and E1 correspondingly. So what it means is gamma is like density is inversely related to volume, and volume is directly related to void ratio. And this is an important relation regarding borrow pit problem. Another thing is, what is the weight of water to be added after compaction? So what is the weight of water to be added in the embankment? That will be found by using this relation, this formula. Weight of water to be added is gamma D1 into V1 into difference between water contents of borrow pit and embankment. So these two relations are important regarding borrow pit problem. Now let's see some other important properties regarding specific gravity. Specific gravity is given by gamma S by gamma W. This we have seen already in the one of the previous formulas. G is equal to gamma S. G is equal to what? Gamma S by gamma W. Gamma S is unit weight of soil solids only, and G ranges from 2.65 to 2.80. And there is another thing called apparent specific gravity, and that will be given by Gm is equal to bulk unit weight divided by unit weight of water. So Gm shall be always less than G. Gm shall be always less than G. In calculations of many things, we use only the specific gravity, not the apparent one. And specific gravity varies accordingly with temperature. Then how to calculate that? Generally we calculate the specific gravity at room temperature or 27 degrees Celsius. So G at 27 degrees Celsius equal to G T degree Celsius into gamma W at T degree Celsius divided by gamma W at 27 degrees Celsius. How it is got? Simply because G gamma W is constant, because gamma s does not vary, so that's why G gamma W is constant. So accordingly we can get this equation. And there is another formula regarding relative density, and relative density is denoted by I suffix d, that is given by E max minus E by E max minus E minimum. What is E here? E is natural void ratio or the existing void ratio, and E max is the void ratio in the loosest state, and E minimum is the void ratio in the densest state. Accordingly we have to calculate the relative density of the soil sample, and it can also be given in terms of unit weights, 1 by gamma minimum minus 1 by gamma. Why? Because we have already seen gamma is inversely proportional to void ratio, so that's why 1 by gamma minimum minus 1 by gamma divided by 1 by gamma minimum or minimum unit weight minus 1 by maximum unit weight. So this is how we have to calculate the relative density. Now we shall see some important formulas regarding water content and how it is determined. First one is oven drying method. By oven drying method we can determine the water content. And what is W1, W2 and W3? W1 is the weight of empty container, W2 is the weight of container and moist soil, and W3 is the container and dry soil. So by using this relation we can get the answer for water content. And there is another important method called pygnometer method. By using this method we can get two values, one is water content and another thing is specific gravity. Both the values can be got by using this method, and first we shall see how specific gravity is got. G is equal to W2 minus W1 by W4 minus W1 minus of W3 minus W4. You can refer this diagram to get to know what is W1, 2, 3 and 4. So W1 is simply the weight of container. So W1 is simply the weight of container, and W2 is the weight of container as well as soil mass, and W3 weight of container and water and the soil mass, all the three together, and W4 is the weight of container and water only. And by using this relation we can get the answer for specific gravity, and by using this specific gravity value in this equation we can get the answer for water content. So WC equal to W2 minus W1 divided by W3 minus W1 into G minus 1 by Z minus 1. And this is an important method regarding the determination of water content and specific gravity. And there is another quickest method to determine water content is the calcium carbide method, and WC is equal to WR by 1 plus WR. What actually is the definition of water content? Water content is given by weight of water to the weight of solids. But in case of calcium carbide method, we will get the water content in terms of total volume. That is, WR is equal to weight of water divided by moist volume or the total volume of soil. So in order to remove, or in order to get in terms of weight of solids, that is weight of water to the weight of solids, we use this formula. W is equal to WR by 1 plus WR, and this is a quickest method to determine water content. And another method is sand bath method, as same W2 minus W3 divided by W3 minus W1. And here also W1 is weight of empty container, W2 is container and moist soil, W3 is container and dry soil. So these are some important methods regarding the determination of water content, and most important is pygnometer method. And now we shall see some formulas regarding particle size analysis. So first and most important formula is the uniformity coefficient and coefficient of curvature. So uniformity coefficient Cu is equal to the ratio of D60 to D10. And what is D60? D60 is the size below which 60% of particles are finer than this size, or that is D60 size by weight, or simply we can say D60 is the sieve size in which 60% particles are passing and 40% is retained. 40% gets retained. So that is the D60 value. And similarly, D10 value goes like this: size below which 10% particles are finer than this size by weight. Or simply we can say the sieve size in which 10% particles are passing and 90% of particles getting retained, and this is called as D10, or we can also call it as effective size. D10 is also called as effective size. This is the coefficient of uniformity, and Cc is the coefficient of curvature, and that is given by D30 square divided by D60 into D10. And there is something called sorting coefficient S0, that is given by S0 is equal to root of D75 by D25, and this formula is very rarely used in case of geotechnical problems. And there is a range for uniformity coefficient and Cc. When Cu is greater than 6 and Cc lies in the range 1 to 3, then we can call that soil, and then we can classify that soil as well graded sand. And in case of Cu greater than 4 and Cc 1 to 3, then that can be classified as well graded gravel. And in case Cu is nearly equal to 1, then that soil will be poorly graded. And this is the Stokes law. The terminal velocity is given by using this formula: V is equal to d square by 18 nu into gamma s minus gamma w, to determine the particle size values. And the Stokes law is valid only when d ranges from 0.2 mm to 0.2 microns. This Stokes law is valid as a sedimentation analysis of particle size analysis, and only when the particle size ranges from 0.2 mm to 0.2 micron. If the particle size is out of this range, we cannot apply this Stokes law. And another method is pipette method. By using pipette method, we can find percentage finer. So percentage n is equal to md by vp minus m dash by v divided by m by v. Md is the mass of dried sample obtained from pipette volume of Vp. So Md is the mass of dried sample and Vp is the pipette volume. And M dash by V is the mass per unit weight of dispersing agent. So mass per unit weight of dispersing agent that we used. And capital M is the total mass of dry soil which is used to prepare the suspension, having a total volume of V. So V is the total volume of suspension and M is the mass of suspension. Total mass of dry soil which is used to prepare the suspension. And next HE by T. HE by T equal to V is nothing but the terminal velocity that is taken from Stokes law. D square by 18 nu into gamma s minus gamma w. These are some important things regarding particle size analysis. Now we shall say the most important thing regarding particle size analysis by using hydrometer. There are some important formulas. First is HE is equal to H1 plus half into H minus VH by AJ. AJ is the area of jar. And H suffix E is the effective depth. And what is H1? H1 is the distance between hydrometer reading and the neck. What is the distance between hydrometer and the neck? That will be called as H1. And small h is the length of hydrometer bulb. So length of hydrometer bulb is the small h value. So in this diagram you can clearly see what is what actually is the h. So here h by 2 and here h by 3. That combining both the things, we can get the length of a bulb, that is denoted by small h. And what is VH? VH by A, here you can see VH by A or AJ, anything else. And GSS is the specific gravity of suspension solid, or we can say specific gravity of soil suspension, that is given by 1 plus RH by 1000. What is RH? RH is the hydrometer reading. And by using these things, we can get the answer for percentage finer. G by G minus 1 rho W V by W into RH by 10. Here GSS is nothing but G. Both are same. G by, that is the specific gravity of soil suspension. G by G minus 1 rho W we know, density of water. And what is V? Total volume of soil suspension. And what is W? Weight of soil mass. And RH is the a corrected reading of hydrometer. And what is the corrected reading of hydrometer? That is given by this RH plus Cm plus or minus Ct minus Cd. What is Cm? Cm is the meniscus correction and it always positive. It is always positive. And what is Ct? Ct is the temperature correction and it can be plus or minus according to the temperature value. If the temperature or the test temperature is above the standard temperature is 27 degrees Celsius. And if it is above the test temperature, then it will be subtracted, and the test temperature above the standard temperature, then it will be added. So accordingly we have to change the sign. And minus dispersion correction. Dispersion correction is always negative. So by applying this much correction, we can get the corrected hydrometer reading. These four formulas are regarding hydrometer, so that we can get the value or answer for percentage N, that is percentage finer. Now we shall see formulas regarding Atterberg's limits. Before moving to formulas, we shall see some definitions of water content. That is, first is liquid limit. Liquid limit is the water content corresponding to 25 number of blows in Cassegrande liquid limit test. And WP is the plastic limit, the water content at which a 3 mm thread of soil crumbles. And WS is the shrinkage limit. It is the smallest water content at which soil mass is completely saturated. You can refer this diagram, volume versus water content. So we can see here solid and semi-solid phase and plastic, and then after liquid limit the soil will be like a slurry. It will have zero shear strength. So this is how varies with accordingly water content. For first, the smallest water content at which completely saturation is shrinkage limit. So after that plastic limit, and after that liquid limit. So WS, that is shrinkage limit, is equal to Wn minus Vn minus Vd by Wd into gamma W. This is an important relation regarding shrinkage limit. So by knowing the natural water content and also the dry volume properties of dry volume, that is volume of dry sample and weight of dry sample, we can get this shrinkage limit value. So Wn, that is natural water content, minus Vn minus Vd by Wd into gamma W. And by knowing Gm and G, that is apparent specific gravity and the specific gravity of soil solids, we can get the answer for Ws. So Ws is equal to 1 by Gm minus 1 by G into 100. And Gm is nothing but gamma D by gamma W. That is apparent specific gravity in terms of dry soil, gamma D by gamma W. And this shrinkage ratio is given by using this formula. Shrinkage ratio is equal to VL minus VP by VD divided by WL minus WP into 100. And this shrinkage ratio shall be equal to apparent specific gravity only at dry state. At dry state, shrinkage ratio is nothing but apparent specific gravity. And there is another thing called volumetric shrinkage. Vs is equal to VL minus Vp by Vd. And another thing is linear shrinkage. Linear shrinkage is given by 1 minus 100 by 100 plus Vs power 1 by 3, that is cube root. And now we shall see some indices: plasticity index, shrinkage index, toughness index, and flow index. So plasticity index is given by WL minus WP, difference between liquid limit and plastic limit. And IS, that is shrinkage limit, is given by plastic limit minus shrinkage limit. And IT is the toughness index, IP by IF, ratio of plasticity index to flow index. And flow index is given by ratio of difference between water content to the corresponding blows. So you can see here in this graph, that is graph regarding water content versus number of blows. So for number of this is a semi-log graph, so that's why WL minus W2 divided by log of N2 by N1. This is how we have to calculate the flow index. And next is the liquidity index, that will be given by Wn minus Wp divided by Ip. And consistency index is Wl minus Wn by Ip, and the summation of both liquidity and consistency indices is equal to 1. And now we shall see more about range of these indices. If plasticity index is equal to 0, then that soil will be non-plastic. If IP is less than 7, then soil will be of low plastic. And if IP is 7 to 17 in this range, then if we can call it as medium plastic soil. And if it is greater than 17, then we can call it as highly plastic soil. And in case of toughness index less than 1, then that soil can be easily friable and crushed. And toughness index gives the shear strength at plastic limit. This is a point to be noted. Toughness index gives shear strength condition at plastic limit. And flow curve also gives an idea of shear strength. Flow curve or the flow index value also gives the idea about shear strength. And if consistency index is 0, then water content will be at what? Will be at WL, that is liquid limit. When the actual water content or the natural water content is already at liquid limit, then consistency index is 0. When consistency index is equal to 1, that means natural water content is at plastic limit. So then only WL minus WP by IP equal to 1. So these are some important things regarding range of indices. And there is another thing called activity. Activity is the ratio of plasticity index to the percentage clay fraction. Now we shall move ahead with the chapter consolidation. So first formula OCR, that is over consolidation ratio, is the ratio of maximum applied stress in past denoted by sigma naught bar to the maximum applied stress at present denoted by sigma bar. And we shall see how to calculate void ratio. There are two methods, height of solids method and change in void ratio method. By using height of solids method, we can determine H's value, that is height of solids is equal to Ws by G gamma W into A. A is the cross-sectional area of soil sample and Ws is the weight of soil solids. So by knowing H's value, we can get the answer for void ratio, that is given by H minus Hs divided by Hs. H is the initial height of the soil sample. And this method, that is del H by H is equal to del E by 1 plus E naught, is the change in void ratio method. So by using this formula also we can determine void ratios. And there are some important definitions regarding compressibility. So AV is the coefficient of compressibility and CC is the compression index. AV is given by the ratio of change in void ratio to the change in effective stress, and CC is given by the ratio of change in void ratio to the log of ratio of two stresses. So because CC is a plot of E versus sigma or the effective stress, where E is in arithmetic scale and sigma bar, that is effective stress, in what scale? Logarithmic scale. So that's why we can get a straight line. But in case of AV, that is coefficient of compressibility, both are in arithmetic scale. So that's why we will get a curve like this. So we will get a curve like this, not a straight line. Actually, a line shall be not like this. So here the straight line can be got using compressibility or compression index. Cc is equal to minus del E by log of sigma 2 bar by sigma 1 bar. And Cc can also be determined using a liquid limit, Cc equal to 0.009 WL minus 10. And this formula is used when clay of undisturbed sample. And Cc equal to 0.007 WL minus 10. This formula shall be used for a clay of remolded sample. When a remolded sample of clay is there, we can use this formula. When an undisturbed sample of clay is there, we can use this formula to determine compression index value without knowing, or with knowing only the liquid limit. And we can also use these two formulas also when we know natural water content or we know initial void ratio. 1.15 into initial void ratio minus 0.35 and 0.0115 into natural water content. So these are the important things regarding compressibility. And there is another important thing called Terzaghis one-dimensional equation. This is the basic equation to determine coefficient of consolidation, time factor, and everything else. So coefficient of consolidation is given by this CV term, and Terzaghi's one-dimensional equation is dou u by dou t, that is partial derivative of degree of consolidation. U is the degree of consolidation, equal to CV into dou square v by dou z square. Z is the height. Now we shall see more about one-dimensional theory. Mv is equal to del v by v naught into del sigma bar. This is a relation regarding Mv. What is Mv? Coefficient of volume compressibility. So we have already seen what AVCC, and this is a new term Mv. Mv is coefficient of volume compressibility. So that's why del v, change in volume to the original volume, divided by del sigma bar, that is change in effective stress. And by knowing mv value, we can determine the settlement, that is the del h. Del h is equal to mv into initial height h naught into effective change in effective stress. And there is a relation between mv and av. Mv is equal to av by 1 plus e naught, that is coefficient of volume compressibility and coefficient of compressibility. Mv is equal to av by 1 plus e naught. And this is a formula regarding total settlement if we know the compression index. So if we know coefficient of volume compressibility, we can use this formula. If we know the compression index, we can use this formula to get the total settlement value. Del h is equal to cc by 1 plus e naught h naught log of sigma f bar, that is final effective stress after external load is applied, that is sigma naught bar plus del sigma bar. Del sigma bar is given by the additional load that is acting over the overburdened soil. So del sigma bar plus sigma naught bar is the sigma f bar divided by sigma naught bar. So by using this formula, we can get the answer for del h, that is total settlement. And this is a relation regarding coefficient of consolidation, and mv coefficient of volume compressibility, and k is the permeability, coefficient of permeability. So these three things are related by using this equation. Cv is equal to k by mv gamma w. These are some important relations. And now we shall see the 1D theory. So TV is the time factor. TV is equal to CVT by d square, and d is the drainage path. D is the drainage path. So if both top and bottom has drainage, then d is equal to total height of sample divided by 2. When only top or only bottom portion has allowance to drainage, then d is equal to h. So accordingly we have to calculate. And TV shall be calculated when we know the degree of consolidation, that is denoted by capital U. So TV is equal to pi by 4 U square when degree of consolidation is less than or equal to 60%. And when it is greater than 60%, TV is equal to 1.781 minus 0.993 log of 100 minus U percentage. So this is the formula regarding TV, that is time factor. And degree of consolidation is given by ST by SU, that is settlement after a time period T divided by ultimate settlement, that is the total settlement. So this is the degree of consolidation. And if there is recompression, then we have to adopt the value of CR, recompression index. CC is compression index and CR is recompression index. So by using this value, we can get the value of del h, that is total settlement. Del h is equal to CR by 1 plus E naught h naught into log of sigma p bar, that is pre-consolidation pressure divided by sigma naught bar, plus this term cc by 1 plus E naught h naught log of sigma f bar usually, and this pre-consolidation stress has to be taken into denominator here. Now we shall see some things about immediate settlement. Immediate settlement, that is SI, after primary consolidation is given by SI is equal to before the primary consolidation is given by SI is equal to h naught by CS log 10. Actually this is log 10, log base 10, and sigma f bar divided by sigma naught bar. And here Cs term is given by using this relation, this formula. Cs is equal to 1.5 recompression index Cr divided by sigma naught bar, and this is only applicable for cohesionless soil. And for cohesive soil, immediate settlement is given by SI is equal to QB into 1 minus nu square by ES. ES is modulus of elasticity, and I is the influence factor, and nu is the Poisson's ratio. And there are something called compression ratios. Ri is the initial compression ratio, Rp is the primary compression ratio, and Rs is secondary compression ratio. So initial compression ratio is given by R0 minus Rc by R0 minus Rf. So what is R0? R0 is the zero dial gauge reading, and Rc is the corrected reading. So in the consolidation meter or odometer, there are dial gauge readings. So R0 is the zero dial gauge reading, and Rc is the corrected reading. R100 is the dial gauge reading after primary consolidation. R100, here you can see. R100 is the dial gauge reading after primary consolidation, and Rf is the final dial gauge reading. So accordingly, we have to use the formula to get the answer for ratios, compression ratios. Ri is the initial compression ratio, Rp primary, Rs secondary, and sum of all the ratios will give 1, will be unity. So now we move ahead to the shear strength. So we completed the formulas regarding properties of soil and consolidation also. Now we shall see formulas under shear strength. So first and basic important formula is the Moore Coulomb theory. Tau is equal to C plus sigma tan phi, or we can say in terms of effective stress. So in terms of effective stresses, tau is equal to C plus sigma bar tan phi dash. So in terms of effective values, and theta f is equal to, that is failure angle, angle of failure plane is given by 45 degree plus pi by 2. And this basic formula can be related to this graph, that is shear stress versus effective normal stress. So this initial intercept, that is here you can see, this is called as cohesion value, and after that a slope is there, and that slope is called as phi, angle of internal friction. This is the Moore Coulomb failure criteria. This is the Moore Coulomb envelope, and the soil below the envelope, or the plane below the envelope is safe, and at the envelope is at the verge of failure, and above this does not exist, because just above the plane the soil gets failed. And there is something called obliquity. Beta max is equal to phi for a granular soil, and phi, and for cohesive soil phi is 0. Then what happens is beta max is also 0. And you can refer to this suggested video to get more about more circle and important relations, that is coming under strength of material chapter also. And this formula is the basic and important thing regarding plastic equilibrium condition. Sigma 1 is equal to sigma 3 tan square into 45 plus pi by 2. What is 45 plus pi by 2? Failure, angle of failure plane. Tan square, theta f or alpha f, anything. So sigma 3 tan square 45 plus pi by 2 plus 2c tan 45 plus pi by 2. This is called as plastic equilibrium condition. And now we shall see formulas regarding triaxial test. In triaxial test, we have confining pressure, deviatoric stress, and also the sigma 1 value. Sigma 1 is given by summation of sigma 3, that is confining pressure and deviatoric stress. And how to calculate deviatoric stress? Sigma d is equal to failure load, or denoted by P divided by area of failure plane, area at failure. And area at failure shall be given by V0 plus or minus del V, change in volume, divided by L0 minus del L, length of the sample at failure, L0 minus del L. And this is only used when there is a consolidated drained condition, or a consolidated drained condition. Only when is the only the test is of this type CD condition, we can use this formula. Or in case of undrained condition, we can use this formula. Undrained condition, you can use this formula because no volume change will be there. For undrained condition, del V shall be 0. So then A naught divided by 1 minus epsilon. What is epsilon here? Epsilon is the strain value. Epsilon is the strain, linear strain. And by conducting UU test, that is unconsolidated undrained test, we can get the value for Poisson's ratio. So Poisson's ratio is denoted by nu is equal to sigma 3 by sigma 1 plus sigma 3. Sigma 3 is the confining pressure. And the Skempton's pore pressure parameters given by B and A. So B is equal to del U3 divided by del sigma 3, and it shall be 1 for saturated soils and 0 for dry soils. And AB is equal to del UD by del sigma D. So AB is equal to del UD by del sigma D, and AB shall be denoted as AF, A suffix F, and A suffix F is not the area of failure. This should not be confused as area of failure plane. So AB is just denoted as AF, and it shall be greater than 1. It shall be greater than 1, or it can also be negative value. And the total change in pore pressure is given in terms of pore pressure parameters, Skempton pore parameters. So del U is equal to B into del sigma 3 plus A into del sigma D. So this is a ultimate formula regarding the Skempton's pore pressure parameters. And now we shall see some other tests like UCC test and vane shear test. So in case of UCC test, that is unconfined compression test, sigma 3 is 0 because of unconfined, no confined pressure is there. So that's why sigma 1 is equal to 2c tan 45 plus 5 by 2. This is a plastic equilibrium condition in case of UCC test. And in case of pure clays, what shall be the sigma 1, how it is related? Sigma 1 is equal to twice undrained cohesion, that will be equal to deviatoric stress, and that is equal to QU, undrained shear strength, that is QU, equal to P by area of failure. And here in this graph you can see the UCC test. So here this is straight and horizontal because phi is 0 for pure clays, and this intercept is CU, that is the radius of Mohr circle. Radius of Mohr circle is CU, and twice the CU is the sigma 1. How? This is the 2 times CU value, 2 times CU. This is the sigma 1. So this is the basic things regarding, these are the basic things regarding UCC. Now we shall see some other things. So this formula, deviatoric stress, area of failure, these things we have already seen in triaxial test itself. Now we shall move on to vane shear test. So in vane shear test, there will be torque acting over the axis. So this torque value will be given by pi d square cu into h by 2 plus d by 6. This formula is applicable when all the top and bottom portion of the veins is immersed in the, or it is underground in the soil. If only bottom portion is underground and top portion is exposed above the ground, then we shall follow this formula. T is equal to pi d square into Cu h by 2 plus d by 12. So these are some basic things regarding consolidation. So from this video we have learned the formulas regarding properties of soil, consolidation and compressibility, and finally the shear strength. So stay tuned, please subscribe the channel right now. Thank you for watching.